Thank you very much. So rather than showing you some very obvious microbially induced sedimentary structures, I will take you to some more dubious ones and more vague ones. And a good example is right here on the starting slide. The importance of them, however, is that they may have a key control on landscape development during the Cambrian. Overview of this talk, I will very briefly introduce the geological storage of CO2 that allows me to do this big project, and show you a little bit about the depositional environment that we reconstructed before I move on to planar sandstone facies that may have these microbially induced sedimentary structures. Then I will have a larger story about the processes that are important for that and show you fewer examples because we only have 4 wells and I do have a poster. And then move on to the conclusions. So the project I work on, we've injected about 1 million tons of CO2 into a Cambrian sandstone. It's about 2.5 kilometers deep. It's working quite well. We've got lots of different branches of science involved in this, and as geologists, we do a combination of producing conceptual models, using statistics and describing the rock, and generating geocellular models to model the CO2 flow, but also microseismicity, which is very important. So the conceptual model, this is where a lot of the microbial-induced sedimentary structures are very relevant. The paleo environment that we reconstructed, that we have in our cores, and on the right-hand side here, I've got a FMI, a micro-resistivity log, which gives you an idea of the sedimentary structures through a fluvial section. We've got a lot of different environments in there. So the block diagram is an interpretation, but we've got a coastal section that is more or less north-south. We've got an east-west trending river that ends up on the coastal section there. And we've got lots of planar facies. And it's the planar facies that they're very important. We have a lot of them, and they are harder to interpret. These planar facies, the planar sandstone facies, are basically composed of 3 different sedimentary structures. We've got straight planar strata that are fairly easy to interpret as wind ripples. We've got some bimodal planar strata that we interpret as deflation lag surfaces, where you've got lots of granules on specific surfaces. A nice example here from Mars, incidentally, because the Cambrian, we did not have vegetation, so we look at a world without. And then we've got these crinkly strata, and we've got a lot of it. You start thinking about things like salt crusts. This is Death Valley. And you start thinking about what effect biofilms may have on this. So here's an example of two sections of core. For your convenience, I've illustrated a few things that might be relevant, but we've got a fair amount of bleaching. Now, this bleaching is basically follows the layering and is quite likely induced by groundwater table at the time. And then we've got a lot of these weird crinkly structures. Some of them are flat at the base and sort of convex at the top. Some of them are more laminated internally, and some of them just seem to drape the surface. So we've got a bit of variability in there. We've got lots of deformation. We've got chips. We've got roll-up structures, or a little Pac-Man structure around here. And we've got coarse-grained fills. Also, importantly, a lot of these crinkly surfaces, these irregular surfaces, are covered by wind-blown sediments that don't seem to erode into this finer material underneath it. So I've produced a poster with more examples, so don't take my word for it, and by all means criticize the interpretation and the language and so on, because that's what we're here for today. But I'll just move on to the sort of the general interpretation here, is that we're capturing silt and clay at the surface, and there's a distinct enrichment. I've produced some SEM images on the poster as well to further back that up. But what we see is the surface irregularities are preserved. We've got wind-blown fills on top. We've got potential desiccation cracks. We've got semi-cohesive deformation, and we've got some chips. So a lot of that is surface hardening, a lot of that is indicative of biofilms and mats. When you look at it in more detail and you start looking in between the individual grains, you start seeing an enrichment in clay, you start seeing a lot of detrital material that is very fine, only a few microns in size, silt and very fine crystalline material. We've got an enrichment in microcrystalline hematite on top of the clay. It is not glauconite. And the strata geometry is unlike adhesion and unlike salt deformation, which you can generate very easily in a tray of sand and salt in your living room. And unfortunately, it's very difficult to interpret also because this is about 500 million years old and it's been cooked thoroughly. When we look at modern analogues to try and interpret the depositional environments, we kind of fall short. So a couple of examples: Nazca Plain, very dry. Namib Desert, also very dry. Distinct interactions of rivers and dunes that we match in our deposits. Marahenses National Park in Brazil, which is coastal. And then you've got some shoals in front of coasts in various locations. But in a lot of these places where we remove the vegetation to allow this interaction of wind-blown sediments and deflation and the development potentially of biofilms, we've got vegetation removing dynamics, if you wish. So a good example, of course, at the coast, we inundate these areas quite frequently and you cannot establish a vegetation there. So we don't really have a good modern analog, which brings us to the processes. So what we can do is we can put a couple of simple things together, but basically say for our microbial surfaces, what we want to have some rainfall, we want the groundwater to basically be at the surface, because if it's too dry, we don't expect them to be there and we expect the sediment to get deflated. And so what you end up with is, you've got your rain, your recharge, and then you've got a groundwater flow. This is a very clean sandstone, so we can use a very simple equation to model the groundwater. And then we've got a river level, which is more or less our base level. So we can play around with these things. The outcome of that is that the geometry of your groundwater surface, which we can then assume is more or less the geometry of your Earth surface, is more or less a climate proxy with very arid environments behaving very differently or having very more flat curves than very wet environments. So there's a potential climate proxy there. There we go. When it comes to the river mobility, because we know we have a river there, obviously the microbial activity is incapable of generating very cohesive banks, and that's been well established. But what we often pass over, what we ignore, is that the sediment supply to these floodplains, if we're adhering sediment to wet areas and deflating it from dry areas, it is the wind that is controlling the deposition and the erosion on the floodplains. So we've got groundwater and wind controlling our floodplains, with the river merely acting as a base level. And that's a very important point because it sets the topographic context for the river. And in this case, when we've got a groundwater curve going up, our topography is not promoting super elevation of the river and therefore avulsions. Unfortunately, the story gets a little bit more complicated because that depends on the deflation of the sediment. And so when we have coarse-grained upstream zones, the sediment of the channel itself is less likely to be deflated, but the floodplain fines are. So we're deflating our floodplain more readily, and we are not deflating our channel. So we increase the amount of avulsions, where the whole channel shifts over to a lower area. And we expect that to be reflected in the sedimentary record as sort of coarse-grained sheet sandstones. When you go further towards the finer grain level, the lowland rivers, what we expect is that we are basically capturing a lot of our sediments there, and we're deflating the levees and we're building up the floodplains by activity of wind and having wet areas where sediment can stick. And then we can put the microbial mats on there to further cement the surface and protect it. And what that will do is it will reduce the amount of avulsions that you will see because there is less super elevation of your river and your floodplains grade along. So we have an increase in the amount of planar floodplain facies that are quite likely sandy and quite likely containing traces of biofilms. And then towards the river mouth, what you start seeing is you're deflating the levees, and it's easier for the channel to shift. So we expect that the river mouth is behaving differently, and we won't see things like bird foot deltas as readily as you would in a finer grained system, or a system where levees are protecting your river channel. So then finally, whatever sediment you're building up in your floodplains, you are not freeing up for desert dune development. So the control that you have in terms of locking up your sediments is very important in terms of how many desert dunes you will see and where you will build sand seas that are aeolian in nature as opposed to fluvial. The silt from this system, because we find very little silt, and there is lots of discussion going on about Precambrian and Cambrian deposits having very little clay and silt, but we also know that the transport distances are much, much larger, which we know from the dust of the Sahara that ends up on our cars here in the UK. So when we have a landscape without vegetation, this becomes a very important dynamic. And you can think about the fertilization of the oceans that it has as an effect, and the biofilms that we create on the land potentially protect some of this silt and prevent it from being deflated. So there's a very subtle balance there in terms of how much silt you can freeing up for dust storms and how much you're actually preserving in the land. But we see very clean sand deposits. We obviously reduce the cohesive strata and the cohesion of riverbanks by removing a lot of the fine-grained material, which is my general suggestion here. And we reduce the volume of deltas by deflating all of this fine-grained material and remaining only with the coarser-grained material. So reduce the volume of lowland rivers and potentially meandering rivers. Which leaves us with two more things. So there's some serious questions here about biofilms. And so first off, how reliable are the interpretations of biofilms from core? And there's been lots of discussion about it. Please come see poster 17 so we can discuss this in more detail and talk about which characteristics are really indicative and which ones will tell us more about surface cementation or which ones don't. Now, and then the second one is, what are the time scales involved with that? So there's a time scale involved with the development and the rejuvenation of a biofilm, which might be in the order of tens of minutes, but there's also a deterioration, a drying up phase. How long do these biofilms protect the ground? And how does that happen when there is lots of sand blowing around and abrasive action going on? We need to match that up against the recurrence of rain, obviously, because if there's only a rainstorm every now and then your biofilm needs to protect the ground for a very long time. If you've got very frequent rainfall, that's a whole different story. Groundwater seepage and also becomes very relevant there, so the general surface of the land. So to just conclude that, the biofilms play a very important role, but a lot of it is unquantified for landscape evolution and the interpretation of the larger scales. But they play an important role in the Cambrian landscape evolution. The interpretation of biofilms in core requires systematic attention, and especially because the modern analogues do not reflect an entire planet without vegetation. And the biofilms are capable of changing the sediment budgets and processes at a global scale. I would like to acknowledge my co-authors, especially Jim Best and Jared Freiberg, absolutely great guys. And then maybe a final thought to close off with is that before vegetation developed on land, it's very difficult to imagine what that would look like. So we've got an image here of Joe Tuciarone. It generates these kinds of art. But typically what we think of is things like volcanoes and degradational rock cliff areas. And very, very rarely do you see a good example of what a depositional system would look like. So modern analogues don't really work. And our analogues from art also don't really work. I'll leave you with that thought.
Quick question, comment?
Using searches for modern analogue, did you look, I forget what the Icelandic term is, but those big outwash plains, they have very little vegetation on them. And,
Yes, the sand-dunes. I definitely looked at the sand-dunes. They're a great combination of processes and a good modern analog, with the exception of the very large floods that are coming through, of which we have no evidence in our system. And also we have no, well, we don't expect there to be any process like that. So the vegetation removing dynamic on the sand dunes in this case is that it's very cold and you've got these giant floods coming through. And so we don't have that per se. And so we have to think about, you know, which processes are compiling our environment. How do you combine everything? And so it's a good one to look at, but it's not a perfect one.
Okay.
Okay.
Oh.
Time for this or not? You mentioned the longevity of EPS and the effects in the desert. Has anyone actually looked at how long binding influence by EPS can be sustained under dry conditions with low bacterial activity?
This is an excellent question for the room.
Okay.